Welcome to Ultimate Sleep Doctor. Tonight, we'll explore a concept that stretches far beyond our everyday experience. The universe, vast and ancient, continues to expand, a graceful, accelerating dance across unimaginable distances. Scientists call it dark energy, a mysterious force driving this expansion, a hidden architect shaping the cosmos. It's humbling to consider the scale of this unseen influence, a reminder of how much remains unknown, yet beautiful in its mystery. Let your thoughts drift with the quiet wonder of it all. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. Just breathe. Let your thoughts drift. Let's begin. Long before telescopes could peek across vast distances, long before we even knew the stars were, in fact, other stars, there was a fundamental puzzle about the cosmos. Astronomers had been observing the night sky for centuries, meticulously charting the positions of stars and planets. They knew these celestial objects moved. The moon danced across the sky, Mars waxed and waned in a predictable rhythm, and the stars, though seemingly fixed, slowly traced out paths across the heavens. But this motion wasn't quite right. It suggested a universe that was, in a way, changing. The earliest observations came from the French astronomer Nicolas Louis Delaunay, way back in 1750. He carefully measured the positions of 22 stars over 6 years and noticed a subtle but significant shift in their apparent locations. This wasn't a simple drift. It was a tiny, gradual movement. However, the observations were hampered by the limitations of the time, poor instruments, imprecise measurements, and a lack of understanding of the scale involved. It was a fascinating observation, but it lacked the precision needed to truly understand what was happening. Then, in the late 18th century, another French astronomer, Joseph Nicephore-Niepce, made a more detailed observation of the star 61 Cygni. He tracked its movement over several years, and while his measurements were still somewhat rough, they provided further evidence that stars weren't simply stationary. This prompted continued interest, but the evidence remained circumstantial, open to alternative explanations based on imperfections in measurements or unknown forces. The real breakthrough came with Edwin Hubble, an American astronomer working at the Mount Wilson Observatory in California during the 1920s. Hubble wasn't just looking at stars. He was meticulously studying galaxies, enormous collections of billions of stars, gas, and dust, held together by gravity. These galaxies appeared as fuzzy patches of light in the telescope's field of view. Hubble's initial task was to catalog these galaxies, creating a comprehensive list and mapping their positions. This was a monumental undertaking, requiring immense patience and dedication. Hubble's crucial observation wasn't simply noticing that galaxies were moving. He discovered a remarkable relationship between a galaxy's distance and its speed of recession. He was using a technique called redshift, a phenomenon that's fundamental to understanding the universe. When light travels through space, the wavelength of that light stretches out, much like a siren sound changes pitch as it moves away from you. This stretching is called redshift, and it's a direct consequence of the expansion of space itself. Hubble realized that the greater the redshift of a galaxy's light, the faster it was moving away from us. He meticulously measured the redshifts of hundreds of galaxies and plotted them against their distances. The result was a strikingly linear relationship, what he termed Hubble's law. The law states simply that the velocity at which a galaxy is receding from Earth is directly proportional to its distance from us. Mathematically, it's expressed as v equals h0d, where v is the velocity, h0 is Hubble's constant, and d is the distance to the galaxy. This meant that not only were galaxies moving away from us, but the speed at which they were moving increased with distance. The farther away a galaxy was, the faster it was receding. It was as if the universe was expanding, and the expansion was happening at a different rate for different galaxies. This wasn't just a random scattering of objects. It was a fundamental property of the universe itself. Hubble's law provided the first solid evidence that the universe was not static, that it wasn't a fixed, unchanging entity. It implied that the universe was, in fact, expanding. This was a revolutionary idea, completely overturning the prevailing view of the time. It's important to note that Hubble didn't discover expansion in the sense of inventing the concept. Scientists had previously suspected something was happening, but Hubble's precise measurements gave the idea considerable weight. The implications of Hubble's law were profound. It suggested that the universe had a finite age, because if it's expanding now, it must have been smaller in the past. This led scientists to begin pondering the question of what might have caused this expansion. What triggered the universe's birth and subsequent growth? Hubble's work laid the foundation for the development of the Big Bang theory, the prevailing cosmological model for the universe. His findings were met with initial skepticism, but the mounting evidence from redshift measurements of other galaxies and the discovery of the cosmic microwave background radiation, a faint afterglow of the Big Bang, gradually solidified the understanding that the universe is expanding. Edwin Hubble's legacy is immense. His careful observations and the simple, elegant equation that resulted continue to be fundamental to our understanding of the cosmos. The story of Hubble's law is not just about a scientist and a set of measurements. It's a story about a shift in perspective, a willingness to challenge established ideas, and the incredible power of observation and mathematical analysis to unlock the secrets of the universe. It's a reminder that even the most profound discoveries often begin with a single, carefully recorded measurement. The early 20th century was a time of incredible scientific breakthroughs, a period where the very foundations of our understanding of the cosmos were being shaken. While Edwin Hubble's work establishing a direct relationship between distance and recession velocity, what we now know as Hubble's law, provided the initial shock, it was the subtle observation of redshift that truly began to unravel the mystery of an expanding universe. Astronomers, primarily working with the new, powerful telescopes being built, were diligently charting the positions and brightnesses of stars across the night sky. They were accustomed to seeing stars appear to wander, or parallax, as the Earth moved around the Sun. This parallax was a fundamental way of measuring distances in our own solar system and even nearby stars. It relied on carefully measuring the apparent shift in a star's position as the Earth changed its vantage point. But when observing incredibly distant stars and galaxies, this method simply didn't work. The parallax measurements became incredibly small, so tiny that they were lost in the uncertainties of the observations. This presented a significant problem. Astronomers needed to know the distances to these faint, distant objects in order to properly interpret their observed brightness. Brightness, combined with apparent size, allowed them to estimate how far away something was. It was like knowing how bright a light bulb is and seeing how dim it appears from across a room. You can start to guess how far away it is. But without a reliable way to measure distance to these distant objects, the data was essentially useless. The faintest objects appeared to be simply fading away as they moved away from us, but it wasn't a simple fading. It was something far stranger. Vesto Slipher, a brilliant but often overlooked astronomer at the Lowell Observatory in Flagstaff, Arizona, was one of the first to truly grasp the significance of this phenomenon. He was meticulously studying the spectra, the patterns of light, emitted by these distant spiral nebulae, which were then thought to be immense clouds of gas and dust within our own Milky Way galaxy. When he analyzed the spectra of these nebulae, he noticed something peculiar. The spectral lines, which were essentially fingerprints identifying the elements present in each object, were shifted towards the red end of the spectrum. This is where the term redshift comes from. The light is stretched, like a siren's sound becoming lower in pitch as it moves away. Now, how does light get stretched? It's a consequence of a fundamental principle of physics. The speed of light is constant for all observers, regardless of their relative motion. Imagine you're on a train throwing a ball forward. To someone standing still outside the train, the ball appears to be moving faster than you threw it. Its speed is added to the speed you imparted. Light is similar. If a light source is moving away from you, the wavelength of the light it emits is stretched along with it, just like the ball. The longer the wavelength, the more red the light appears. Slipher's observations showed that almost all of the spiral nebulae had redshifted spectra, meaning they were all moving away from us. What was truly remarkable was the degree of redshift. The further away a nebula appeared to be, the greater the redshift. This wasn't just a slight shift, it was a dramatic stretching of the light. Slipher painstakingly measured the redshifts of dozens of these nebulae, and his data consistently showed a linear relationship. The farther away the nebula, the greater the redshift. This observation alone suggested something profoundly unusual was happening. It wasn't simply that these nebulae were receding. They were receding at an accelerating rate. The prevailing belief at the time, however, was that these nebulae were simply clouds of gas and dust within our own galaxy, and that their apparent recession was simply a consequence of their movement within the Milky Way. But Slipher's work, combined with the observations of other astronomers, began to suggest a radically different explanation. In 1929, Arthur Eddington, a prominent British astronomer, presented a paper summarizing Slipher's findings and linking them to Hubble's distance measurements. Eddington argued that the observed redshift was best explained if the entire universe was expanding. This wasn't expansion within the nebula, It was expansion of the space itself. It was as if the universe was inflating, carrying the galaxies along with it, like raisins in a rising loaf of bread. The galaxies weren't moving through space. Space itself was expanding, carrying the galaxies along for the ride. This was a truly revolutionary idea, challenging the long-held assumption that the universe was static and unchanging. The implications of this expansion were enormous. It meant that the universe was far older than previously thought. It also opened the door to the possibility that the universe wasn't just expanding, but that something, a mysterious force, was driving this expansion. The initial observations of redshift, meticulously made by Vesto Slipher, provided the crucial piece of evidence that launched the modern era of cosmology, setting the stage for the discovery of dark energy and our current understanding of the expanding universe. It was a story not of a single event, but of careful observation, painstaking analysis, and a willingness to question everything we thought we knew. The prevailing picture of the universe, established in the mid-20th century, was one of a cosmos that, while expanding, maintained a remarkably consistent level of density. This idea arose as a compelling alternative to the burgeoning theory of the Big Bang, which proposed a violent beginning to the universe from an extremely hot and dense state. The Big Bang, with its associated notions of cosmic inflation and the evolution of the universe over billions of years, seemed to require a tremendous amount of explanation, a complex chain of events to explain where everything came from and how it got here. In contrast, the steady-state theory offered a beautifully simple solution, a universe that wasn't changing significantly over time, despite its overall expansion. The core of the steady-state model, championed primarily by George Lemaitre and Herman Bondi, Arthur Koch and Thomas Gold, rested on a fundamental principle. The universe was, and always would be, essentially unchanging on a large scale. It wasn't growing from a single origin point, but rather maintaining a constant density by continuously generating matter. This wasn't a sudden, explosive creation. Instead, it was a perpetual, gradual process. Throughout the universe, new matter, specifically hydrogen atoms, was spontaneously appearing from seemingly nothing. This wasn't a violation of the laws of physics, as the process was thought to be driven by quantum fluctuations, tiny, random variations in energy that, according to the uncertainty principle, could momentarily manifest as particles and antiparticles. The mechanism for this creation was described as space creation, a concept difficult for many to fully grasp. It wasn't like factories churning out matter, but rather a continuous, though incredibly subtle manifestation of energy into matter. The rate of this creation was extraordinarily low, estimated to be about 1 hydrogen atom per cubic meter per billion years. However, as the universe expanded, this newly created hydrogen filled the increasing vacuum, maintaining a constant average density. To accommodate this continuous creation, the theory demanded the existence of a mechanism, often termed cosmic equivalent of evaporation, that would perpetually replace the matter lost due to the expansion. The observational data of the time, while limited by the technology available, provided a surprisingly strong initial boost to the steady-state model. Particularly significant was the detection of the cosmic microwave background, CMB, radiation in 1964 by Arno Penzias and Robert Wilson. Initially, the CMB was interpreted as a confirmation of the steady-state theory. The theory predicted a faint, uniform background radiation, a residual heat from the early, hot universe, and the CMB precisely matched this prediction. This was a major victory, as it provided a concrete, observable signature of the universe's earlier state, a state that the steady-state theory was able to explain. Furthermore, the steady-state theory aligned well with observations of distant galaxies. The theory predicted that galaxies should appear roughly the same at all redshifts, meaning that the universe should look similar regardless of how far away you looked. This was partly because the continuous creation of matter was thought to smooth out any significant density fluctuation that might have existed in the early universe. The theory suggested that these fluctuations were not just random variations, but rather the seeds of structure that were gradually being diluted by the constant influx of new matter. However, the story didn't end there. As more observations accumulated, a troubling discrepancy began to emerge. Astronomers, using increasingly sophisticated instruments, started to detect subtle variations in the density of the universe. These variations, or anisotropies, were extremely small, a few parts in 1,000, but they were undeniably present. These anisotropies were, in essence, a confirmation of what the Big Bang theory had predicted, that the early universe had undergone significant density fluctuations, the seeds of galaxies and galaxy clusters. The steady-state theory struggled to account for these observed anisotropies. The continuous creation of matter, while capable of diluting density variations, couldn't fully erase them. The theory lacked a robust explanation for why these fluctuations were so small and why they were clustered in a particular pattern. The observed temperature fluctuations in the CMB, initially interpreted as anisotropies, were also inconsistent with the simple, uniform prediction of the steady-state model. Moreover, as radio astronomy advanced, astronomers discovered a much higher density of galaxies in the distant, high redshift universe, the universe at the earliest times. This was entirely contrary to the steady-state prediction of a uniform distribution of galaxies across all redshifts. The observed abundance of early galaxies seemed to support the idea of a universe that had indeed undergone a significant transformation from a denser, more chaotic state to the more homogeneous state we observe today. The growing body of observational evidence, the anisotropies in the CMB, the observed abundance of early galaxies, steadily eroded the foundation of the steady-state theory. While initially, the theory was a compelling alternative to the Big Bang, the universe stubbornly refused to cooperate. The scientific community, slowly but surely, began to shift its allegiance towards the Big Bang model, a model that ultimately offered a far more comprehensive and accurate explanation of the observed universe. Fritz Zwicky wasn't a household name then, not like Hubble or Einstein. He was a young, brilliant and remarkably eccentric astrophysicist working at the California Institute of Technology in the 1930s. He had a passion for the unusual, a persistent curiosity that often led him down paths less traveled by his contemporaries. His primary focus was galaxy clusters, enormous collections of hundreds or even thousands of galaxies bound together by gravity. These were fascinating objects, and Zwicky, unlike many of his colleagues, suspected that what they appeared to be based on their velocities was simply incomplete. He began his work with the Small Magellanic Cloud, a dwarf galaxy orbiting our own Milky Way. Using observations of the velocities of individual galaxies within this cloud, Zwicky calculated how much mass was needed to keep them from flying apart. He was using a technique then considered quite advanced, measuring the Doppler shift of light emitted by these distant galaxies. The faster a galaxy moves towards you, the blue-shifted its light becomes. Conversely, a galaxy moving away from you appears red-shifted. Zwicky meticulously charted the speeds at which the galaxies were moving within the Small Magellanic Cloud. His calculations, based solely on the observed velocities, produced a startling result. The mass required to hold the cluster together, to keep those galaxies from escaping, was dramatically larger than the mass that could be accounted for by the visible matter, the stars, gas, and dust that we could see through telescopes. He estimated that the cluster needed about 1,700 times more mass than was actually observed. This was a significant discrepancy, a colossal missing chunk of something unseen. He described it as a missing mass. Zwicky initially suspected errors in his measurements, but he painstakingly checked his calculations repeatedly. He considered various explanations. Perhaps the stars were much more massive than he thought, or perhaps the gas was emitting light we weren't detecting. However, none of these solutions adequately explained the magnitude of the discrepancy. He published his findings in 1937, presenting a compelling argument for the existence of a substantial amount of mass that was invisible to conventional telescopes. His paper was met with skepticism, largely because it challenged the prevailing understanding of gravity and the structure of the universe. Many scientists considered his results to be a mistake, perhaps due to observational errors. Intrigued by Zwicky's work, he turned his attention to more massive galaxy clusters, notably the Virgo cluster, which was then considered the most massive cluster known. The Virgo cluster, located about 54 million light-years away, contained hundreds of galaxies, each moving at incredibly high speeds. Zwicky, employing similar velocity measurements, arrived at an even more dramatic conclusion. The mass needed to keep the Virgo cluster from dissolving was estimated to be approximately 600 times greater than the mass he could detect through visible light. He dubbed this elusive mass dark matter, a term he coined to describe this unknown substance. This wasn't the first time the concept of dark matter had been discussed. Some astronomers had speculated about unseen mass affecting galactic rotation, but Zwicky's repeated and forceful arguments, bolstered by his meticulous work with galaxy clusters, propelled the idea into the forefront of astrophysical thought. He was essentially saying, there's something out there, something we can't see, that's exerting a gravitational influence far stronger than anything we're observing directly. Zwicky's work wasn't immediately accepted, and he faced considerable criticism. His methods were seen as unconventional, and the concept of a vast, invisible mass holding galaxies together was unsettling. However, his persistence and the consistent nature of his results began to shift the perspective of some scientists. He continued to refine his calculations and explore the implications of his findings. Importantly, Zwicky's investigations were conducted at a time when the prevailing cosmological models were based on a static universe, one that didn't expand or contract. His observations, coupled with the increasing evidence of galaxy rotation curves, that galaxies rotate faster at their edges than predicted by the visible mass alone, provided a growing body of evidence that suggested the universe was far more complex and dynamic than previously imagined. Zwicky's pioneering work, although initially dismissed, laid the crucial groundwork for the eventual acceptance of dark matter and, ultimately, the understanding of dark energy. His legacy lies in recognizing that the universe holds secrets beyond what our telescopes can directly perceive. His observations, made decades before the advent of sophisticated telescopes and computer simulations, continue to be a cornerstone of our current understanding of the cosmos. The universe, after its explosive birth, the Big Bang, wasn't immediately a smooth, uniform place. It was a seething, opaque soup of incredibly hot plasma. This plasma was a chaotic mix of particles, electrons, protons, and photons, all constantly interacting, bouncing off each other with every collision. These photons, the very seeds of light, were relentlessly scattered, meaning they couldn't travel very far. Like trying to see through a dense fog, light was absorbed and re-emitted countless times, making the early universe completely opaque to observation. It was a brilliant, blinding mess. For the first 380,000 years or so, this state continued. The universe was expanding, yes, but this expansion wasn't accompanied by any significant change in its overall temperature. It remained extraordinarily hot, a constant, intense glow. Then something remarkable began to happen, a shift that would ultimately reshape our understanding of the cosmos. As the universe continued to expand, it also continued to cool. This cooling wasn't a gentle decrease, it was a dramatic transition. Eventually, the temperature dropped to a point where electrons and protons could finally combine, forming neutral hydrogen atoms. This was a pivotal moment. Before this happened, photons couldn't exist freely. Now, with far fewer free electrons to scatter off, the photons were able to travel across the universe without being constantly bumped around. They streamed freely for the first time. This event is often referred to as recombination, though it's more accurately described as the last scattering of the primordial photons. The photons released during this last scattering didn't disappear. Instead, they continued to travel, carrying information about the universe at that incredibly early stage. And just like the light from a distant star, they've been stretching along with the expansion of the universe. This stretching has dramatically lowered their energy, shifting them from visible light to longer wavelengths, ultimately becoming microwaves. This stretched radiation is what we now detect as the cosmic microwave background, CMB. The CMB is essentially a faint afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. It's remarkably uniform in temperature, approximately 2.725 Kelvin, which is 270.45 degrees Celsius. This incredible uniformity is one of the most compelling pieces of evidence supporting the Big Bang theory. It's like a baby picture of the universe, frozen in time. However, the CMB isn't perfectly uniform. Subtle variations, tiny temperature fluctuations, exist across its surface. These fluctuations, initially incredibly small, smaller than a billionth of a degree, represent density variations in the early universe. Think of them as the seeds from which galaxies and large-scale structures eventually grew. The slightly cooler regions were slightly denser, and gravity pulled more matter into them. Scientists have meticulously mapped these fluctuations with incredible precision, using telescopes like the Planck satellite and ground-based observatories. The patterns within the CMB aren't random. They follow specific statistical distributions, revealing a universe that was initially almost perfectly smooth, but seeded with these small, primordial density variations. These variations represent the initial conditions for the formation of the cosmos we see today. The amplitude, the size of these fluctuations is crucial. They provide a direct measure of the density fluctuations present in the early universe. And importantly, the observed size of these fluctuations is consistent with the predictions of the Big Bang model, particularly when combined with our understanding of inflation. The period of extremely rapid expansion that occurred in the very first fractions of a second after the Big Bang. Analyzing the CMB allows us to determine several key properties of the universe, including its geometry, whether it's flat, open, or closed. Measurements of the CMB strongly suggest that the universe is remarkably flat. This flatness is a critical constraint on cosmological models. Furthermore, the CMB provides an estimate of the total energy density of the universe, the density of all its components, including matter, radiation, and dark energy. This measurement is consistent with the lambda-CDM model, the standard model of cosmology, which includes dark matter and dark energy. Importantly, the CMB isn't just a historical record. It continues to evolve. As the universe expands, the wavelengths of the CMB photons are stretched further, shifting them towards lower frequencies. This ongoing stretching will eventually make the CMB undetectable by current instruments. However, studying the CMB remains a powerful tool. Scientists continue to refine their measurements and search for subtle clues that might reveal even more about the early universe, including potential evidence for alternative cosmological models or new physics beyond the standard lambda-CDM paradigm. The CMB, a faint whisper from the dawn of time, continues to hold the key to unlocking some of the universe's deepest secrets. The universe, as we've begun to understand it, wasn't always the vast, expanding space we observe today. Our story so far has established that the rate of this expansion isn't constant, a fact that challenges simpler models of the universe. We've seen evidence suggesting a period of incredibly rapid growth in the early moments after the Big Bang, and now we're going to explore a revolutionary idea, one that proposes a brief, explosive phase built directly into the fabric of spacetime itself. This is the concept of inflation. The problem with the standard Big Bang model, as it stood, was its struggle to fully account for certain observations. For instance, the universe appears remarkably uniform. The density of matter and energy is almost identical across vast distances. This uniformity is incredibly difficult to explain if the universe began with just a tiny, hot, dense seed and then gradually expanded. It's like trying to create a perfectly smooth, round sphere using only a handful of pebbles. The initial imperfections would have magnified over time. Then there's the issue of the cosmic microwave background, that faint afterglow of the Big Bang. The CMB is remarkably uniform, but it also has tiny, subtle fluctuations, slight variations in temperature. These fluctuations are the seeds of all the structure we see today: galaxies, clusters of galaxies, and so on. The problem is, the standard Big Bang model predicted fluctuations that were much more random, a kind of white noise in the temperature distribution. The observed fluctuations were too patterned, too regular, to be easily explained. Enter Alan Guth and Andre Lind in the 1980s. They independently developed the theory of cosmic inflation, a radical idea that suggested the universe underwent a period of exponential expansion in its earliest moments, a tiny fraction of a second after the Big Bang. Before this inflationary period, the universe wasn't simply expanding. It was growing at a rate that's almost incomprehensible. Imagine a balloon being inflated, but instead of inflating at a gradual pace, it starts inflating at a dramatically increasing rate, doubling in size every fraction of a second. That's the essence of inflation. The driving force behind this incredible expansion wasn't anything we're familiar with. It wasn't matter or energy in the conventional sense. Instead, it was a field, a sort of quantum field called the inflaton. This inflaton possessed enormous energy, and this energy, according to Einstein's theory of general relativity, caused spacetime itself to stretch and expand. It's a truly bizarre concept. Space wasn't just getting bigger. The very geometry of space was being warped and distorted by this energy field. The key mechanism at play was a process called slow roll. The inflaton field initially had a large potential energy, like a ball at the top of a hill. As the universe expanded, the potential energy decreased, but it did so slowly, allowing the expansion to continue at a nearly constant rate. This slow roll behavior is what gave inflation its characteristic exponential growth. Think of it like a perfectly smooth, gradually sloping hill. A ball rolling down it maintains a relatively constant speed. Crucially, inflation wasn't a permanent state. As the universe expanded, the inflaton field eventually lost its energy and decayed, transitioning into a different phase of evolution. This transition marked the end of inflation and the beginning of the standard Big Bang expansion, but it left a profound imprint on the universe. The evidence for inflation is, frankly, compelling. The observed uniformity of the cosmic microwave background fluctuations is a direct consequence of inflation. The rapid expansion smoothed out any initial irregularities, stretching them across vast distances. The tiny quantum fluctuations that existed during inflation were then magnified and stretched, becoming the seeds for all the large-scale structure we see today. It's like zooming out on a photograph of a turbulent sea. The individual waves become less prominent, and the overall pattern of swells and currents becomes apparent. Furthermore, inflation predicts a specific ratio between the density of matter and energy in the universe, a ratio that closely matches what we observe. This is known as the flatness problem, and inflation elegantly solves it. Without inflation, the universe would have to be incredibly fine-tuned to be as flat as it is. A slight variation in the initial conditions would have led to a drastically different universe. Of course, inflation isn't without its challenges. It's still a theoretical framework, and scientists are actively searching for direct evidence, perhaps through observing primordial gravitational waves, ripples in spacetime generated during the inflationary period. Detecting these gravitational waves would provide undeniable proof of inflation and revolutionize our understanding of the universe's very beginning. While many questions remain, cosmic inflation represents a monumental step forward in our quest to unravel the mysteries of the cosmos, offering a remarkable explanation for the universe's origin and its astonishingly smooth and uniform structure. The universe, as we began to understand it, wasn't quite the static, unchanging realm proposed by some early thinkers. The early 20th century saw a revolution in astronomy, driven by observations that simply didn't fit with existing models. Edwin Hubble's work, meticulously measuring the redshifts of distant galaxies, a phenomenon revealing their recession, provided the first concrete evidence that the universe was expanding. This expansion wasn't a gentle stretching, it was accelerating, suggesting a force was pushing everything further apart at an increasing rate. This discovery spurred a frantic search for the nature of this driving force. The standard model that emerged, combining several key observations and theoretical frameworks, became known as the lambda-CDM model. The lambda in the name comes from the Greek letter lambda, often used to represent a constant, and it signifies the cosmological constant. This cosmological constant was initially introduced by Einstein as a way to allow for a static universe. However, when Hubble's observations of expansion emerged, Einstein famously called the cosmological constant his greatest blunder. Ironically, it was later resurrected and refined to address the accelerating expansion. The CDM, parts of the model refer to cold, dark matter and cosmological dynamics, respectively. Let's delve deeper into what this comprehensive model posits. The lambda-CDM model essentially describes the universe as composed of roughly 68% dark energy, 27% dark matter, and only 5% ordinary matter, the stuff we're made of: atoms, stars, galaxies, and everything visible. The model's success lies in its ability to accurately predict a wide range of observations, from the cosmic microwave background to the large-scale structure of the universe. It's not just a pretty theory. It's a remarkably precise description of reality based on a wealth of data. The key to understanding the role of dark energy within this framework is to consider the universe's evolution. In the very early universe, immediately after the Big Bang, the expansion was dominated by the initial rapid expansion driven by the energy released during that event itself. This phase, often referred to as inflation, represents a brief but incredibly energetic period, far exceeding the conditions that exist today. As the universe expanded and cooled, this initial energy began to dissipate. However, something remained, a mysterious force that continued to drive the expansion and, crucially, to accelerate it. The cosmological constant, dark energy, isn't a force in the traditional sense like gravity. It's more accurately understood as a property of space itself. General relativity, Einstein's theory of gravity, describes gravity as a curvature of space-time. Dark energy, according to the model, is causing space-time to expand, and this expansion isn't slowing down. It's increasing in rate. Think of it like inflating a balloon. As you blow air into it, the surface stretches, and the distance between points on the surface increases. Dark energy is creating an analogous effect on the very fabric of the universe. The model relies heavily on computer simulations to predict the large-scale structure of the universe. These simulations start with the initial conditions, the temperature fluctuations observed in the cosmic microwave background. And then, using gravity as the dominant force, they allow the universe to evolve over billions of years. Dark matter plays a crucial role in these simulations, providing the gravitational scaffolding that pulls together galaxies and galaxy clusters. Without dark matter, the simulations would produce a universe far too smooth and uniform. The accelerating expansion driven by dark energy has profound implications for the future of the universe. If the expansion continues unabated, the observable universe will become increasingly empty. Galaxies will move farther and farther apart, eventually receding beyond our ability to see them. Eventually, the observable universe will effectively shrink as light from distant objects will never reach us. This isn't an immediate process. It's a gradual unfolding over trillions of years. However, the nature of dark energy remains one of the biggest mysteries in modern cosmology. The leading candidate is a form of energy inherent to the vacuum of space itself, often referred to as quintessence. But even with this possibility, the precise explanation for dark energy's existence and behavior is still elusive. Furthermore, the precise value of the cosmological constant is significantly smaller than theoretical predictions based on quantum field theory, presenting a considerable challenge to physicists. The lambda-CDM model isn't a perfect description. It doesn't explain the nature of dark matter, and it requires several fine-tuning adjustments to match observations perfectly. Nevertheless, it provides the most successful framework for understanding the universe's past, present, and to a significant degree, its future. It's a testament to the power of scientific inquiry, a continuous process of observation, theoretical development, and refinement. The ongoing research into dark energy, driven by ambitious projects like the Dark Energy Survey and the Euclid mission, promises to unlock some of the universe's deepest secrets, pushing the boundaries of our understanding of space, time, and the very nature of reality. The quest to understand dark energy is a profound exploration, mirroring our fundamental desire to comprehend our place within the vast and enigmatic cosmos. It's a journey of discovery that will undoubtedly shape the future of cosmology and our understanding of the universe itself. The late 1990s were a time of incredible shifts in our understanding of the cosmos, driven largely by a team of astronomers working with a deceptively simple idea. Look at distant supernovae. Barry Mador, then a graduate student at the University of Washington, was a key member of this group, and their work, centered around a project known as the Supernova Cosmology Project, began to unravel a perplexing mystery. Before this, cosmologists believed the universe's expansion, initiated by the Big Bang, was gradually slowing down. Gravity, after all, is a powerful force, pulling everything together. The expectation was that the initial thrust of the Big Bang would diminish over time, leading to a universe that would eventually contract in a big crunch. However, the supernovae observations began to paint a radically different picture. The team's approach was remarkably straightforward. Supernovae, particularly type Ia supernovae, are incredibly useful standard candles. These explosions are remarkably consistent in their intrinsic brightness, meaning they all emit a predictable amount of light. Because of this consistency, astronomers could measure how bright a type Ia supernova appears to be from Earth. This apparent brightness is affected by distance. The further away an object is, the fainter it appears. By comparing the apparent brightness to the known intrinsic brightness, astronomers could calculate the distance to the supernova. This wasn't a new technique, of course. Astronomers had been using supernovae to measure distances across the universe for decades, but the team focused on a specific region of the sky, a relatively small patch of the southern sky centered around the Virgo cluster of galaxies. They meticulously identified and tracked hundreds of type Ia supernovae that had exploded in this region. They weren't just looking at a handful of these events. They were collecting data on a truly massive scale. As the data accumulated, a startling trend emerged. The distances to these supernovae were significantly greater than what the conventional models predicted. Based on the then current understanding of the universe's expansion rate, the supernovae should have appeared dimmer than they actually did. The distances measured were consistently larger than expected, suggesting that these supernovae were further away than they should have been, given their apparent brightness. The implications were profound. The only logical explanation for this discrepancy was that the universe's expansion wasn't just continuing, it was accelerating. It wasn't just expanding, it was speeding up. This acceleration contradicted everything that had been assumed about gravity's role in the universe's fate. The idea was so unexpected, so counterintuitive, that it initially met with considerable skepticism. The team, including Mador, published their findings in 1998, and the results quickly reverberated throughout the astronomical community. Other research groups, using independent datasets, began to arrive at similar conclusions. The evidence for an accelerating expansion was mounting. The supernova cosmology project's work provided the first robust, statistically significant indication that something entirely new was at play in the universe. The nature of this something remained a mystery. It couldn't be accounted for by any known force, like gravity or electromagnetism. The acceleration implied the existence of a repulsive force, an energy density that was counteracting gravity and pushing the universe apart at an increasing rate. This unknown force was dubbed dark energy, a term coined to describe this mysterious component of the universe. The acceleration wasn't uniform. The expansion rate wasn't constant. It was changing over time. It had been slower in the early universe, but then, roughly 5 billion years ago, it began to pick up speed. This transition point, while not fully understood, is a critical element in the story of dark energy. It's a time when the universe shifted from a slower expansion to an increasingly rapid one. Furthermore, the acceleration wasn't just a local phenomenon. It was happening throughout the observable universe. Astronomers could measure the expansion rate in distant galaxies, and the results consistently pointed to this accelerating expansion. It wasn't just a quirk of a particular region. It was a fundamental property of the universe itself. The discovery, largely thanks to Barry Mador's meticulous work and the Supernova Cosmology Project, revolutionized our understanding of cosmology. It forced scientists to confront the possibility that the universe is dominated not by matter and energy, as previously believed, but by a mysterious, unseen force, dark energy. The implications extend far beyond simply understanding the expansion of the universe. It raises fundamental questions about the ultimate fate of everything. The accelerating expansion suggests a universe that will continue to expand indefinitely, growing colder and emptier with each passing moment. It's a humbling and profound realization, one that reminds us just how much we still don't know about the grand, intricate workings of the cosmos. The universe, as we've been piecing together, is expanding. It's not just expanding, it's expanding at an ever-increasing rate, a truly surprising discovery. For a long time, scientists had assumed expansion would be slowing down, perhaps due to the gravitational pull of all the matter within it. But observations, particularly those made by Barry Mador and his team, revealed the opposite. This discrepancy, this unexpected acceleration, demanded an explanation, and that's where the Type Ia supernova came into the story. These supernovae aren't like most supernovae. They aren't the result of a massive star running out of fuel and collapsing in a spectacular explosion. Instead, Type Ia supernovae involve a specific and remarkably consistent process. They occur in binary star systems where one star is a white dwarf, the dense, remnant core of a star that has already gone through its life cycle, and the other is a companion star, often a red giant. The key to understanding why Type Ia supernovae are so useful lies in the white dwarf itself. White dwarfs, once they've exhausted their nuclear fuel, aren't held up by the outward pressure generated by fusion reactions. Instead, they're supported by something called electron degeneracy pressure. This pressure arises from the quantum mechanical principle that electrons cannot occupy the same energy state in the same space. It's a fundamental rule of the universe at its smallest scales, and it creates an incredibly strong resistance to further compression. However, this stability is delicate. As the white dwarf gains mass, often by stealing material from its companion star, it approaches a critical limit. This limit is known as the Chandrasekhar limit, approximately 1.4 times the mass of our Sun. When the white dwarf surpasses this limit, the electron degeneracy pressure can no longer withstand the inward pull of gravity. The star undergoes a runaway nuclear fusion reaction, detonating in a brilliant and incredibly uniform explosion. What makes these supernovae so special is the predictability of this explosion. Because the underlying process is so consistent, a white dwarf reaching the Chandrasekhar limit and triggering a complete fusion reaction, the brightness of a type Ia supernova at its peak is remarkably similar across different events. It's not simply a matter of the explosion being bright. The amount of light produced during that peak is tightly controlled. This consistency is the foundation of what scientists call a standard candle. Think about it like this. If you have a flashlight that always shines at the same intensity, regardless of how you use it, you can easily determine its distance. You simply measure how bright it appears to you, and knowing that brightness allows you to calculate how far away it is. Type Ia supernovae act like these incredibly reliable flashlights in the cosmos. Astronomers began meticulously measuring the apparent brightness of these supernovae. The apparent brightness is how bright an object appears to us from Earth, influenced by both its intrinsic brightness and its distance. By comparing the measured apparent brightness with the known, consistent peak brightness of the supernovae, scientists could calculate their distances. The dimmer a type Ia supernova appears, the farther away it must be. This measurement technique, known as standard candles, revolutionized our understanding of the universe's expansion. Initially, the measurements indicated a slowing expansion, but as more and more type Ia supernovae were observed, a startling trend emerged. The expansion wasn't slowing down, it was accelerating. The farther away the supernovae were, the faster they were receding from us, suggesting that the expansion rate was increasing over time. These measurements provided the first compelling evidence for dark energy, a mysterious force driving this acceleration. If the universe is expanding at an increasing rate, then there must be something pushing it apart, something beyond the gravitational pull of matter. Dark energy, initially just a theoretical concept, began to gain traction as the most plausible explanation. The distance to these supernovae had to be determined independently, too, providing another crucial piece of the puzzle. This was done using techniques like Hubble's law, which states that galaxies are receding from us at a speed proportional to their distance, and through observations of distant galaxies, redshift. The redshift is the stretching of light waves as objects move away from us, a direct consequence of the expansion of space itself. The more redshifted the light, the greater the distance. Scientists used these independent distance measurements to compare them with the accelerating expansion rate inferred from the supernovae. The results were incredibly precise, further solidifying the role of dark energy. The more precise the measurements of Type Ia supernovae, the more convincingly dark energy's influence was revealed. The continued study of Type Ia supernovae, along with other observations, continues to refine our understanding of dark energy and its role in shaping the ultimate fate of the universe. It's a story still being written, one supernova at a time, offering a breathtaking glimpse into the vast and dynamic nature of reality. The universe is a truly vast place, and understanding its size, its true extent, has been a persistent puzzle for astronomers for centuries. Initially, measuring distances in space felt like trying to gauge the size of a distant ocean with only a small ruler. Our immediate surroundings, our solar system and nearby stars, we could measure with relative ease. But as we looked further and further out beyond the familiar, things became increasingly complicated. The simple linear relationship between distance and brightness, which worked so well for nearby stars, began to break down. This was a problem because brightness is directly related to a star's size and temperature, and these properties change dramatically as stars age. Fortunately, astronomers recognized that there were specific types of stars whose brightness clearly correlated with their intrinsic properties, their absolute brightness. These stars acted as crucial stepping stones, offering a way to build a cosmic distance ladder. The first of these were Cepheid variable stars. Cepheids, named for the mythological queen, exhibit a fascinating phenomenon. Their brightness fluctuates predictably over time. They pulse, growing brighter and dimmer in a repeating cycle, and the period of this cycle, the time it takes for one complete brightening and dimming, is directly related to their intrinsic luminosity, or how bright they actually are. This relationship isn't a coincidence. It's a remarkably consistent one. Astronomers discovered that a Cepheid's period luminosity relationship is exquisitely regular, allowing them to determine a star's true brightness with high accuracy. The clever part is that by observing a Cepheid's period, we can instantly calculate its absolute luminosity. Then, by comparing this intrinsic brightness with the observed brightness of the Cepheid as seen from Earth, we can determine its distance. It's like having a brightness meter that tells us exactly how far away a star is. The beauty of using Cepheids lies in their use as standard candles. Each Cepheid, thanks to its predictable period luminosity relationship, represents a standard. The longer the period, the further away the Cepheid. Henrietta Leavitt, a brilliant astronomer at the Harvard College Observatory in the early 20th century, made this connection incredibly clear. She meticulously plotted the period luminosity relationships of dozens of Cepheids, uncovering a linear correlation that had been largely overlooked. This discovery was revolutionary. It wasn't enough just to find this relationship. Astronomers needed to use it to measure distances to galaxies far beyond our own. This involved a technique known as the distance-rung method. The first significant use of Cepheids as standard candles came with Edwin Hubble's work in the 1920s. Hubble used Cepheid variables in the Andromeda galaxy, our nearest large galactic neighbor, to demonstrate that Andromeda wasn't simply a brighter version of our Milky Way. Instead, it was a separate, independent galaxy located millions of light years away. This was a landmark achievement, fundamentally changing our understanding of the universe. However, using Cepheids to measure distances to even more distant galaxies presented a challenge. The further out you went, the fainter the Cepheids appeared, making them harder to observe accurately. The period luminosity relationship, while reliable, becomes less precise at extreme distances. The faintness introduces uncertainty. Another powerful tool in the distance-rung method is the tip of the red giant branch, TRGB technique. This method utilizes a different type of aging star, red giant stars. As red giant stars burn through their hydrogen fuel, their outer layers expand and cool, giving them a reddish hue. The core of the star becomes increasingly hot and dense, eventually leading to a point known as the tip of the red giant branch. This tip represents the maximum luminosity a red giant star can achieve during its evolution. Just like Cepheids, the brightness of a star at the TRGB is directly related to its intrinsic luminosity. Because the process of reaching the TRGB is so well understood, astronomers can precisely determine a star's absolute luminosity based on its position at the TRGB. The TRGB method is particularly useful for measuring distances to galaxies that are too faint for Cepheids to be easily observed. It's essentially using the brightest red giants as standard candles. The TRGB method has become increasingly important in recent years, particularly with the advent of large sky surveys like the Dark Energy Survey and the Rubin Observatory's Legacy Survey of Space and Time, LSSD. These surveys are detecting thousands of TRGB stars and galaxies across the universe, allowing astronomers to build an even more robust distance scale. The data collected from these surveys is not only helping us to understand the structure and evolution of the universe, but also, critically, testing the assumptions underlying our cosmological models, including the nature of dark energy. By comparing distance measurements obtained with Cepheids and the TRGB, scientists can rigorously assess the accuracy of these techniques and refine our understanding of the cosmos. The universe, as we've come to understand it, isn't a smooth, featureless expanse. It's a record, a faint echo of its incredibly early moments, imprinted upon the fabric of space itself. To decipher that record, scientists have developed clever techniques, each relying on subtle patterns revealed through incredibly precise measurements. One of the most powerful of these techniques is rooted in something called baryon acoustic oscillations, or BAO for short. These oscillations aren't visible to the eye, but their effects are measurable, offering a remarkably consistent distance scale that can be used to probe the expansion history of the universe. The story begins billions of years ago, just a few 100,000 years after the Big Bang. The universe was a hot, dense soup of particles, primarily protons and electrons, collectively known as baryons. This early universe wasn't uniform. It was bubbling with tiny density fluctuations. These fluctuations arose from quantum fluctuations in the very fabric of space-time itself, amplified by the interplay of gravity. Now, gravity, as you might recall, pulls things together. Where there were slightly denser regions, gravity pulled even more matter towards them. Conversely, regions slightly less dense experienced a weaker pull. These density fluctuations weren't random. They existed in a specific pattern, a sort of cosmic ripple effect. This pattern arose because the speed of sound, or more precisely, the speed of light through the plasma, was the fastest thing in the early universe. Light, being massless, travels at the ultimate speed limit. However, the baryons, being massive particles, traveled at a significant fraction of that speed. The photons, light particles, constantly scattered off of these baryons, effectively creating a sound wave that propagated through the plasma. This wave traveled at a speed close to the speed of light, but not quite. As the universe expanded, this sound wave, this bow, stretched along with it. Imagine a slinky being pulled out. The waves get longer, but their spacing remains constant. This stretching process, driven by the expansion of the universe, imprinted a characteristic scale on the distribution of matter. The distance scale is remarkably well defined, approximately 150 megaparsecs. That's roughly 480 million light years, a truly vast distance. Yet this specific separation holds true across the observable universe. Scientists can measure the apparent size of these bow features at different distances. The key is to observe how the positions of galaxies are clustered together at different redshifts. Redshift, as you've learned, is a measure of how much the light from a distant galaxy has been stretched due to the expansion of the universe. A higher redshift means the galaxy is more distant, and its light has been stretched more. By carefully analyzing the clustering patterns of galaxies at various redshifts, astronomers can determine the apparent size of the bow scale. If the observed clustering size matches the expected 150 megaparsec scale, it's a strong indication that the universe is expanding uniformly, at least on large scales. If the observed clustering is significantly different, it suggests that the expansion rate has changed over time, offering a direct way to test cosmological models. The James Webb Space Telescope, with its incredible sensitivity, has been particularly valuable in this endeavor. It can detect faint galaxies at extremely high redshifts, allowing for precise measurements of bow at the very early stages of the universe. The telescope's ability to peer back in time is revolutionizing our understanding of the early cosmos. Furthermore, bow isn't just about mapping the expansion history. It's a crucial tool for measuring the density of the universe. The scale of bow is intimately linked to the density of the ordinary matter, the baryons, that make up the universe. By accurately measuring the bow scale, scientists can constrain the amount of matter in the universe and test competing theories about dark matter and dark energy. The beauty of bow as a cosmological ruler lies in its independence. Unlike some other distance indicators, bow isn't reliant on a standard candle, a single object with a known luminosity. Instead, it uses the inherent structure of the universe itself as a benchmark. It's a robust and versatile tool, providing a fundamental constraint on our understanding of the cosmos. Current research is focused on refining these measurements, particularly at higher redshifts, where the bow signal is strongest and less contaminated by other effects. Scientists are utilizing large galaxy surveys, like the Dark Energy Survey and the Rubin Observatory's Legacy Survey of Space and Time, LSST, to map the distribution of galaxies over vast areas of the sky. Each new observation strengthens the case for the standard cosmological model, the lambda-CDM model, which posits that the universe is dominated by dark energy and cold dark matter. Ultimately, the continued study of baryon acoustic oscillations offers a profound window into the birth and evolution of the universe, and its measurements continue to shape our vision of the cosmos's grand story. The universe, as we've been learning, isn't just expanding. It's expanding at an accelerating rate, a truly bizarre and baffling phenomenon. We've used supernovae, distance indicators based on pulsating stars, and the subtle echoes of the Big Bang, the baryon acoustic oscillations, to understand this expansion and infer the existence of something we call dark energy. But how do we know dark energy is out there? And more importantly, how do we actually map it? That's where weak lensing enters the story, offering a completely different approach to seeing the unseen. Weak lensing builds upon the concept of gravitational lensing, Einstein's famous equation showing how gravity bends light. A massive object, like a galaxy or a cluster of galaxies, acts like a lens, warping the space around it. Light from a distant galaxy, traveling across the vast gulf of space, is subtly bent as it passes by this intervening mass. This bending doesn't just distort the image, it causes the distant galaxy's light to appear slightly stretched and smeared across the sky. Now, imagine a vast, seemingly empty field of galaxies. Each of these galaxies is emitting light, and that light is being subtly distorted by the gravitational pull of every other galaxy in the universe. It's like a cosmic game of dominoes, where the gravity of one galaxy influences the way light from countless others appears to us on Earth. The effect is incredibly weak, hence the name weak lensing. But it's there, meticulously shaping the images of distant galaxies. The key is that this distortion isn't random. The amount of stretching and smearing a galaxy experiences depends directly on the mass of the intervening object that's causing the lensing. A massive galaxy cluster, for example, will cause a much stronger lensing effect than a small, isolated galaxy. Furthermore, the orientation of the distortion is also linked to the alignment of the foreground mass with our line of sight. Think of it like shining a flashlight. The light beam will naturally bend slightly due to the curvature of the air. Astronomers don't simply look at individual distorted images. Instead, they collect images of millions, even billions of galaxies. They then use sophisticated computer algorithms to analyze these images and measure the tiny distortions, changes in the shape of the galaxies themselves. These algorithms are incredibly powerful, detecting changes in shape fractions, tiny deviations from a perfect circle. A galaxy that appears slightly elliptical, for example, is experiencing weak lensing. The more distorted the galaxy, the more accurately we can determine the mass of the lensing object. But the real magic happens when we combine this information with our understanding of the universe's large-scale structure. We know that dark matter, which makes up about 85% of the universe's total mass, doesn't interact with light. It doesn't emit, absorb, or reflect it. However, it does exert a gravitational force, and that force is what causes the lensing. By meticulously mapping the distortions in the shapes of millions of galaxies, we can effectively see through the visible matter and map the distribution of dark matter. The distortions themselves act as a proxy for the unseen mass. The more concentrated the dark matter, the more pronounced the lensing effects will be. This allows us to build a 3D map of the dark matter distribution across vast regions of the sky. This isn't just a theoretical exercise. Weak lensing is providing increasingly precise constraints on the properties of dark energy. The way dark energy affects the expansion rate of the universe influences the growth of these large-scale structures, and therefore, the amount and distribution of dark matter we observe through weak lensing. Furthermore, weak lensing allows us to study the formation and evolution of these structures. By comparing the observed lensing patterns with simulations of the universe's evolution, we can test different models of dark energy and refine our understanding of how the universe has changed over time. The data is exquisitely sensitive to subtle variations in the dark energy equation of state. That is, how the dark energy density changes over time. The field of weak lensing is constantly evolving, with new telescopes and surveys like the Dark Energy Survey and the upcoming Euclid mission, collecting ever larger datasets. As these datasets grow, they will provide an even more detailed and accurate picture of the universe, ultimately helping us to unlock the secrets of dark energy and the underlying nature of spacetime itself. It's a slow, meticulous process, but one that offers a unique and powerful way to explore the cosmos, revealing the unseen through the distortions of light. The universe is, in a very real sense, revealing itself to us, one distorted galaxy at a time. The universe, as we've explored, is expanding. It's not just expanding, it's expanding at an accelerating rate. This realization, built upon decades of careful observation and increasingly precise measurements, presented a profound puzzle. We knew gravity should be slowing down this expansion, pulling everything back together like a cosmic handbrake. But instead, it felt like something was pushing outwards, resisting gravity's pull. To understand this accelerating expansion, cosmologists needed a way to quantify this mysterious force, a way to describe its behavior. That's where the equation of state, often denoted by the Greek letter W, entered the picture. The equation of state is essentially a mathematical relationship that connects the pressure and density of a substance. It's a remarkably simple concept, borrowed from thermodynamics, but its application to the universe is extraordinarily complex. In our everyday world, we're familiar with the equation of state of gases like air or water. For example, for a perfect gas, the equation of state is PV equals nRT, pressure P, volume V, the number of moles N, the ideal gas constant R, and temperature T. However, the universe isn't a collection of ordinary gases. It's dominated by dark energy, a substance we can't directly see or touch, and its behavior is far stranger than anything we encounter locally. What makes W so important is that it tells us how dark energy's pressure relates to its density. It's not just a single number, It can change over time and across vast distances. Initially, cosmologists assumed that W would be a constant value, perhaps equal to -1. This would correspond to what's called a cosmological constant, the idea that dark energy is an inherent property of space itself, a uniform energy density permeating all of existence. If W were -1, then the pressure of dark energy would exactly balance its density, resulting in a constant expansion rate, a universe that simply keeps getting bigger and bigger forever. However, the best data we have doesn't strongly support this simple scenario. The most crucial piece of evidence came from observations of Type Ia supernovae. These supernovae are incredibly consistent in their brightness, making them excellent standard candles for measuring distances across the cosmos. By comparing their observed brightness with their calculated intrinsic brightness, astronomers could determine their distances, and consequently, the distances to the galaxies hosting them. The supernovae data revealed that the expansion rate of the universe was slower than predicted if dark energy were simply a cosmological constant. This indicated that W was not exactly -1. The data suggested that W was slightly less than -1. This meant that dark energy's pressure was actually negative, a truly bizarre concept. Negative pressure implies that dark energy is exerting a kind of tension or outward force, pushing against gravity and accelerating the expansion. The exact value of W is still uncertain, but current measurements, primarily from the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, consistently point to a value of approximately -1.98 to -1.99. This is a surprising result, and one of the biggest mysteries in cosmology. Now, the implications of this value of W are profound. If W remains constant, then the expansion rate will continue to accelerate indefinitely. However, some theoretical models suggest that W could evolve over time. This means that the amount of dark energy, and therefore the acceleration of the expansion, might change as the universe ages. Perhaps W is initially closer to -1, gradually becoming less negative as the universe expands. This would mean that the expansion would slow down at some point in the distant future, though it would still remain faster than a constant expansion. There's another, even more radical possibility, that W isn't constant at all, but changes in a complex and unpredictable way. Some theoretical models involve quintessence, a dynamic, evolving dark energy field. Quintessence could be influenced by the gravitational interactions of other components of the universe, creating a feedback loop that alters its properties over time. The current data doesn't favor this picture, but it leaves open the possibility that our understanding of dark energy is fundamentally incomplete. Furthermore, the value of W has significant consequences for the ultimate fate of the universe. If W remains constant and less than -1, then the universe will continue to expand forever, becoming increasingly cold and empty as galaxies drift apart at ever-increasing speeds. This scenario is often referred to as the Big Rip, a dramatic, catastrophic finale where the accelerating expansion eventually tears apart all matter, from galaxies to atoms. However, if W were to change sign and become positive, then the expansion would eventually reverse, and the universe would begin to contract, ultimately collapsing in a big crunch. The precise value of W is therefore intimately tied to the long-term destiny of our universe. It's a value we continue to refine with more precise measurements, striving to unlock the secrets of dark energy and ultimately, the grand narrative of cosmic evolution. The ongoing quest to determine the value of W is not just an exercise in measuring distances. It's a fundamental investigation into the nature of space, time, and the very forces that govern our universe. It's a story that's still being written, one measurement at a time. The prevailing view in cosmology for decades had been remarkably simple. The universe wasn't just expanding, it was expanding at an accelerating rate. This acceleration, this mysterious dark energy, accounted for roughly 68% of the universe's total energy density. But a small group of physicists and astronomers, persistent and increasingly confident, began to question this straightforward explanation. They argued that the observations, particularly the rotation curves of galaxies, hinted at something profoundly different, something that didn't require invoking a completely new, unknown form of energy. This is where modified Newtonian dynamics, or MOND, enters the story. The idea originated with astronomer Vera Rubin in the 1970s. Rubin was meticulously studying the rotation curves of spiral galaxies, those swirling collections of stars, gas, and dust. A rotation curve, when plotted, shows how the orbital speed of stars and gas around a galaxy changes with their distance from the galaxy's center. Based on the amount of visible matter, stars, gas, dust, we'd expect a curve that decreases with distance. The further out you go, the slower things should rotate, much like planets in our solar system. After a certain distance, the rotation speed should essentially flatten out. This is because the gravitational pull weakens as you move further away, and the orbital speed is determined by that gravitational force. However, Rubin's observations consistently showed something utterly unexpected. The rotation curves of galaxies, particularly those in the outer reaches, remained remarkably flat. The stars and gas were orbiting at roughly the same speed, regardless of their distance from the galactic center. It was as if they were holding onto an enormous, unseen force, preventing them from slowing down as predicted by Newtonian gravity. This was a significant discrepancy, a fundamental challenge to our understanding of gravity. MOND attempts to resolve this anomaly without introducing dark energy. Instead of assuming the existence of a mysterious force driving the acceleration, MOND proposes a radical revision to Newton's law of gravity itself. Specifically, it suggests that Newton's law breaks down at very low accelerations, the kind experienced by objects far from the center of a galaxy. MOND postulates that gravity becomes stronger at these low accelerations. The core of MOND's formulation is expressed through an empirically determined scaling law. This law dictates the precise relationship between the observed acceleration and the Newtonian acceleration. It essentially says that when the acceleration is low, gravity becomes significantly stronger than what Newtonian gravity predicts. The constants in this scaling law are determined by fitting the observed rotation curves of galaxies. Let's consider a simple example. Imagine a small object orbiting a much larger, unseen mass. According to Newtonian gravity, the object's orbital speed would be determined solely by the mass and distance. But within MOND, the gravitational force is artificially amplified at low accelerations, effectively increasing the orbital speed. This isn't a new force, it's a modification of the existing gravitational law. The initial success of MOND was largely based on its ability to accurately predict the rotation curves of spiral galaxies, many of which had been meticulously measured by Rubin and others. It provided a compelling, albeit unsettling, alternative to dark energy. However, MOND wasn't without its own challenges and criticisms. One of the biggest hurdles was its lack of a complete theoretical framework. MOND was initially developed as an empirical adjustment, a mathematical patch to fix the observed rotation curves. It didn't offer a fundamental explanation for why gravity should behave differently at low accelerations. The underlying physics remained enigmatic. Furthermore, MOND struggled to explain observations beyond the solar system. It performed well within galaxies, but it had difficulty accounting for the behavior of stars and gas in globular clusters, dense, spherical collections of stars. Observations of these clusters, which exhibited a broader range of accelerations, presented a problem for the simple scaling law. More sophisticated versions of MOND, like TVS, tensor vector scalar gravity, were developed to address these shortcomings. TVS incorporates additional terms into the theory, introducing new fields to better explain the diverse accelerations observed in different astronomical objects. However, even these extensions haven't achieved the same level of broad acceptance as the standard dark energy model. The debate between dark energy and MOND continues to this day. While dark energy remains the dominant paradigm, MOND offers a viable, testable alternative. Recent research, particularly concerning the dynamics of dwarf galaxies and the large-scale structure of the universe, has fueled renewed interest in MOND, highlighting the complexities of gravity and the ongoing quest to truly understand the cosmos. It underscores the fact that our understanding of the universe is still evolving, and that sometimes the most profound discoveries come from challenging the established assumptions. The prevailing models of dark energy, largely built around the concept of a cosmological constant, a uniform energy density permeating all of space, had been remarkably successful in explaining the accelerating expansion of the universe. However, decades of observations and theoretical work began to hint at something far more dramatic, a far more unsettling possibility. If the constant expansion wasn't simply a passive stretching of space, but a relentlessly increasing acceleration, it suggested the energy itself was evolving, changing over time. This led scientists to consider the idea of phantom energy. Phantom energy is a hypothetical form of dark energy where the equation of state, represented by the parameter W, isn't just a constant value of -1, as in the cosmological constant. Instead, W can be less than -1. This seemingly small difference carries profound consequences for the universe's future. While a W of -1 implies a constant energy density, a W value less than -1 signifies that the energy density increases as the universe expands. It's as if dark energy isn't just spreading out, but actively growing in strength. The implications are staggering. If phantom energy dominates, the expansion rate of the universe wouldn't simply increase steadily. It would accelerate without limit. The driving force behind this extreme expansion isn't just the inherent push from the growing energy density, but a fundamental property of the energy itself. This growing energy pushes space-time apart with ever-increasing force, leading to a scenario known as the Big Rip. The Big Rip isn't a gentle, gradual unveiling of the cosmos. It's a catastrophic, violent event, playing out on a scale almost incomprehensible. As the energy density continues to rise, the force of expansion becomes so immense that it begins to overcome all binding forces within the universe. First, it would start by disrupting galaxies, tearing them apart as their gravitational forces are no longer sufficient to hold their stars together. Then, the expansion would continue, ripping apart the individual galaxies, before ultimately affecting the larger structures like galaxy clusters and superclusters. The fabric of space-time itself would be stretched and torn, fundamentally altering the very structure of the universe. The distances between objects would grow infinitely fast, leading to the complete disintegration of everything, from the largest cosmic structures to the smallest atoms. The calculations involved in modeling the Big Rip are extraordinarily complex, relying heavily on general relativity and incorporating the evolving behavior of phantom energy. Physicists use sophisticated simulations, constantly refining their understanding as new observational data emerges. The key lies in precisely determining the value of W and how it changes over time. Currently, the observational data, primarily from Type Ia supernovae and baryon acoustic oscillations, definitively support a phantom energy scenario. However, the possibility remains, and it's a critical area of ongoing research. One of the significant challenges in testing the Big Rip hypothesis is that the timescale for its onset is incredibly long, trillions of years. We're talking about a future so far removed from our own that it's difficult to envision. By that point, our own civilization, and indeed the universe as we know it, would have ceased to exist. Furthermore, the precise behavior of phantom energy is highly sensitive to its fundamental properties. Variations in the equation of state, even small ones, can dramatically alter the predicted timeline for the Big Rip. Some models predict a crossover scenario, where phantom energy transitions into a more conventional form of dark energy, perhaps a cosmological constant, before the full dramatic acceleration unfolds. This transition would necessitate a fundamental shift in our understanding of the universe's evolution. Scientists are exploring various approaches to constrain the phantom energy paradigm. They're looking for subtle signatures in the cosmic microwave background, CMB, the afterglow of the Big Bang. These signatures could reveal information about the early behavior of phantom energy, offering clues about its precise equation of state, precise measurements of the growth of structure in the universe, the way galaxies and clusters of galaxies have formed over time, also provide valuable constraints. Another avenue of investigation involves searching for evidence of exotic physics at extremely high energies, potentially observable through gravitational wave astronomy. If phantom energy interacts with gravity in unique ways, these interactions could manifest as detectable ripples in space-time. The development of more powerful telescopes and gravitational wave detectors offers the potential to probe the universe's deepest mysteries and perhaps, one day, provide a definitive answer regarding the fate of the cosmos. Ultimately, the question of whether the universe is destined for a big rip or whether a more benign fate awaits remains one of the most profound and unanswered questions in cosmology. It represents a humbling reminder of the limits of our current knowledge and the vastness of the universe, a constant invitation to explore and discover. The prevailing cosmological model, the lambda-CDM model, had become remarkably successful in explaining many of the observations about our universe's expansion. However, it still faced a profound mystery: dark energy. It wasn't simply a placeholder for something unknown. The data strongly suggested a dynamic component to this energy, one that wasn't constant. This led scientists to explore alternative ideas, moving beyond the static lambda term and investigating what if dark energy wasn't just a fixed pressure, but something that changed over time. The initial breakthroughs in this area stemmed from the concept of quintessence. Quintessence, initially proposed by physicists like Simon Stebbings in the 1980s, was a radical shift in thinking. Instead of viewing dark energy as a constant, like a uniform, unchanging pressure-filling space, quintessence suggested that it could be a dynamic, evolving field, much like the electromagnetic field or gravity itself. This field, often represented by a scalar field, meaning it has no spatial components, would permeate all of space, and its energy density and pressure would fluctuate over cosmic time. The core idea was rooted in the possibility that the vacuum of space itself isn't truly empty. It's a potential reservoir of energy, existing in a quantum state of minimal energy. When the universe expanded rapidly in its early moments, a period known as inflation, this field might have undergone a phase transition, like water changing from liquid to gas. This transition would have released a tremendous amount of energy, driving the accelerated expansion we observe today. Now, a crucial aspect of quintessence models is the equation of state, represented by the parameter W. While lambda has a value of exactly -1, quintessence allows W to vary. This is where things became incredibly complex and fascinating. Researchers began to explore models where W was not constant, but changed depending on the energy density of the field. One particularly influential model, introduced by Alan Guth and his colleagues, involved a scalar field with a potential energy landscape resembling a Mexican hat or a funnel. The shape of this potential dictated how the field's energy density changed as the universe expanded. As the universe grew, the field's energy density decreased, pulling the value of W closer to -1. However, the key was that it didn't reach -1 permanently. Instead, the field's interactions with itself, would cause it to oscillate, effectively rolling around the top of the funnel. This rolling motion resulted in fluctuations in the energy density and, consequently, changes in the value of W. These oscillations generated an effective cosmological constant, contributing to the accelerated expansion. But crucially, the oscillations meant that the acceleration wasn't a smooth, constant process. It was a more complex, time-varying effect. Different variations of the quintessence model explored various shapes for the potential energy landscape, each resulting in a different pattern of oscillations, and therefore, a different evolution of W over cosmic time. Some models predicted that W would have been closer to -1 in the early universe, gradually decreasing as the universe expanded and the field's energy density diminished. Another important aspect of these models was the influence of the cosmological constant itself. The constant term in Einstein's equations represented a gravitational constant, but within the quintessence framework, the cosmological constant could be interpreted as the energy density of the quintessence field at the present time. This allowed for a more nuanced picture of dark energy's origin and evolution. Furthermore, quintessence models didn't simply consider a single scalar field. Several researchers investigated scenarios involving multiple scalar fields interacting with each other. These interactions created even more complex dynamics, allowing for a richer and potentially more accurate description of the universe's expansion. The mathematical equations describing these interactions grew considerably more complicated, requiring sophisticated numerical simulations to understand the system's behavior. The exploration of quintessence models wasn't without its challenges. One of the primary difficulties was the lack of a compelling theoretical motivation for the existence of these scalar fields. Unlike the cosmological constant, which emerged as a natural consequence of general relativity, the quintessence fields were often introduced as ad hoc additions to the model, without a clear underlying physical mechanism. Despite this, the models provided a flexible framework for understanding the observed accelerated expansion. They successfully reproduced the data from supernovae observations, which had initially triggered the dark energy hypothesis, and they offered a dynamic alternative to the static lambda model. The pursuit of quintessence models spurred further research into the fundamental nature of dark energy and the physics governing the vacuum of space. Researchers continually refined the models, incorporating new observational data and exploring different potential energy landscapes. The quest to understand dark energy continues, and quintessence models remain a vital component of the ongoing search for a deeper understanding of our universe's fate. The ability to vary W and to explore time-dependent dynamics offered a pathway to a far more detailed picture of dark energy's influence on the cosmos. Ultimately, the ongoing investigation into quintessence models highlights the inherent challenges in cosmological research. The need to combine theoretical insights with observational evidence, to grapple with concepts that stretch the limits of our current understanding, and to constantly refine our models as new data emerges. It represents a tenacious effort to answer one of the most profound questions facing modern science. What is the nature of the dark energy driving the expansion of the universe? The universe, as we've come to understand it, isn't just a big, expanding blob of galaxies drifting apart. It's a remarkably intricate, layered structure, and the story of its formation is inextricably linked to the mysterious force we call dark energy. For a long time, cosmologists considered the expansion of the universe driven purely by the initial bang, a rapid outward push from the Big Bang itself. But observations, particularly those involving distant supernovae, revealed something far more peculiar. The expansion wasn't just happening, it was accelerating. This acceleration hinted at a fundamental property of space itself, a repulsive force counteracting gravity on the largest scales. This acceleration has profound implications for how structures like galaxies and galaxy clusters formed. Without dark energy, gravity would have long ago halted the expansion, pulling everything back together into a more compact, uniform state. Instead, dark energy provides a constant outward pressure, essentially pushing space itself apart. This isn't a force in the traditional sense, it's more like a property of spacetime itself, an inherent tendency for space to expand. The early universe was incredibly dense and hot, a plasma of fundamental particles. Tiny fluctuations in density, almost imperceptible variations in the distribution of matter, existed within this plasma. These fluctuations were amplified by the relentless expansion. Think of it like dropping pebbles into a still pond. The initial ripples quickly grow and distort the surface. Dark energy, by relentlessly stretching space, acted as a seed for these initial fluctuations. The larger the fluctuations became, the more space grew around them, further magnifying their density. This process is often referred to as inflation, although it's crucial to understand that inflation, as originally conceived, involved a period of extraordinarily rapid expansion driven by a different mechanism. In this context, dark energy's effect is a slower, more sustained expansion that allows these density fluctuations to develop into the large-scale structures we observe today. These amplified density fluctuations began to collapse under their own gravity, forming the first dark matter halos, vast regions dominated by dark matter. Dark matter, as we've discussed, plays a crucial role in gravitational attraction, essentially scaffolding the formation of these halos. However, dark energy is the architect, determining the scale of the structure. Within these dark matter halos, ordinary matter, protons, neutrons, and electrons, eventually began to coalesce, drawn together by gravity. These halos then served as gravitational wells, attracting and holding together the gas and dust from which the first stars and galaxies were born. The precise shape and size of the resulting galaxies were, in part, influenced by the expansion rate dictated by dark energy. Galaxies formed in regions where the density fluctuations were particularly pronounced, amplified by the ongoing stretching of space. The distribution of galaxies in the universe, the cosmic web, is a direct consequence of this interplay. Massive filaments of galaxies, separated by vast voids, create a network of interconnected structures. These filaments are areas where the density fluctuations are highest, areas where the outward push of dark energy is slightly weaker, allowing gravity to dominate and pull matter together. Furthermore, dark energy affects the evolution of these structures over time. As the universe expands, the density of matter decreases, but dark energy's density remains relatively constant, maintaining a steady outward pressure. This means that while gravity is still working to pull things together, dark energy's influence grows more dominant over billions of years. Computer simulations of the universe's formation rely heavily on incorporating dark energy's effects. These simulations demonstrate that without dark energy, the universe would look dramatically different, far more uniform, with fewer large-scale structures and a much lower density of galaxies. The observed cosmic web, with its intricate filaments and voids, is a direct reflection of the influence of this mysterious force. Looking ahead, the ongoing expansion, driven by dark energy, will continue to reshape the universe. Galaxies will continue to move apart, and the cosmic web will continue to evolve. The ultimate fate of the universe, whether it will expand forever or eventually slow down and collapse, is intimately tied to the nature and behavior of dark energy. Scientists are actively pursuing experiments and observations, from studying the light from distant supernovae to mapping the distribution of galaxies, in an effort to understand this force and unravel the secrets of the universe's evolution. It's a grand, ongoing story, one that's still being written, and dark energy remains a crucial, albeit enigmatic, character. The expansion of the universe, once a relatively slow and gentle stretching, is accelerating. This isn't a sudden, dramatic explosion, but a continuous, relentless pushing outwards, driven by something we call dark energy. The implications of this accelerated expansion are profound, reaching far beyond our current understanding of cosmic timescales. We've explored several scenarios: the possibility of a catastrophic ripping apart by an overly energetic dark energy, or variations based on dynamically changing dark energy fields. But one scenario, arguably the most consistent with the observed data, paints a remarkably stark picture of the universe's eventual fate: heat death. This isn't a dramatic, fiery apocalypse, but a chillingly silent one. The continued expansion, unchecked by any opposing forces, means that galaxies are moving farther and farther apart at ever-increasing speeds. Light, traveling at the universal speed limit, simply cannot keep up with this expansion. Galaxies that are currently visible to us, those within our observable universe, will eventually recede beyond our ability to see them. Their light will be stretched to such extreme wavelengths, effectively becoming undetectable, as space itself expands between us and them. It's like watching a distant ship sail away, not because it's moving faster, but because the ocean between you and it is growing wider and wider. As galaxies disappear from view, the universe becomes increasingly empty. The space between these distant, unreachable structures is not just empty in terms of matter, it's empty of photons as well. The photons released by stars, supernovae, and any other processes generating light are relentlessly stretched by the expansion, losing energy in the process. Eventually, the universe will be dominated by a very low-energy background radiation, a faint, almost imperceptible glow, a remnant of the Big Bang itself, but one so redshifted and diluted by the expansion that it will be practically impossible to detect. This background radiation represents the last vestiges of the initial heat released during the universe's birth. The fundamental laws of physics, as we currently understand them, dictate that energy tends to disperse, to spread out. There isn't a mechanism within the standard model to concentrate energy, to create pockets of higher density. As the expansion continues, the energy of the universe is inexorably diluted. Stars will eventually burn out, not because of a lack of fuel, but because the gravitational attraction between stars and their surroundings will be too weak to sustain nuclear fusion. The last embers of stellar fusion will fade, leaving behind only remnants, white dwarfs, neutron stars, and black holes. These objects themselves will eventually decay, though the timescales involved are staggeringly long, far exceeding the current age of the universe. Even black holes, considered the most stable objects in the cosmos, are not immune to theoretical processes like Hawking radiation, where they slowly emit particles and gradually lose mass over unimaginable periods. The process of dilution continues relentlessly. As energy becomes more dispersed, the differences in temperature between regions of the universe diminish. The universe approaches a state of thermodynamic equilibrium. There are no more temperature gradients to drive useful work, no more processes to convert energy into different forms. All energy is spread uniformly throughout space at a very, very low level. This uniform distribution of energy is the essence of heat death. Consider a hot cup of coffee cooling down. Initially, there's a significant temperature difference between the coffee and the surrounding air. This temperature difference drives heat flow from the coffee to the air, until the coffee and the air reach the same temperature thermal equilibrium. The universe, in its heat-death scenario, is like that coffee, but on a scale far grander than anything we can truly comprehend. The universe has expanded so much that its size is effectively infinite, and the tiny amount of energy remaining is so incredibly low that any attempt to extract useful work is futile. It's important to note that heat death doesn't necessarily imply a complete absence of activity. Quantum fluctuations, inherent in the very fabric of spacetime, would continue to occur. Particle-antiparticle pairs would spontaneously appear and disappear, governed by the uncertainty principle. However, these fluctuations would be incredibly small, incredibly rare, and would contribute no useful energy to the overall system. They represent a chaotic, random dance of particles in a fundamentally empty and cold universe. The very laws of physics themselves, as we understand them, would effectively cease to have any significant influence on the grand scale. The time scale for this heat death is almost unimaginably vast. The expansion of the universe is accelerating, and the rate of this expansion is determined by dark energy. Based on current observations, the universe will continue to expand indefinitely, and the heat death scenario will unfold over a period that is far, far longer than the current age of the universe, trillions upon trillions of years. It's a future so distant that our minds struggle to grasp its magnitude. Ultimately, the universe will become a vast, cold, empty void, a silent testament to the relentless march of expansion and the inevitable decay of all things. It's a sobering thought, perhaps, but also a profoundly beautiful one. A final, elegant conclusion to the story of the cosmos. The universe, as we've discussed, is expanding. This expansion wasn't a sudden, explosive event, but a gradual stretching, like a balloon being inflated. For a long time, scientists assumed that this expansion was slowing down, pulled back on itself by the very gravity that held galaxies together. Gravity, after all, is a force of attraction. It's what keeps us on Earth and what causes planets to orbit stars. The idea was that the combined gravity of all the matter in the universe would eventually win the tug-of-war, and the expansion would decelerate. However, observations made in the late 1990s shattered this expectation. Two independent teams studying distant Type Ia supernovae, incredibly consistent stellar explosions used as standard candles, discovered something truly remarkable. The expansion wasn't slowing, it was accelerating. This discovery was initially met with profound surprise, forcing scientists to grapple with a fundamental puzzle about the nature of the universe. The accelerating expansion implied the existence of a mysterious force, something pushing outwards, counteracting gravity's inward pull. This wasn't a force in the traditional sense, like electromagnetism or gravity itself. Instead, it was a property of space itself, a repulsive effect inherent within the fabric of space-time. This concept led to the introduction of dark energy, a name that quickly became synonymous with one of the greatest unknowns in modern cosmology. It's important to note that dark doesn't mean evil or sinister. It simply means we don't yet understand its composition or nature directly. We can only infer its existence based on its effects. The challenge, however, wasn't just to know that dark energy was there. It was to understand what it was. Initially, many models proposed that dark energy was simply a modification of Einstein's theory of general relativity, a correction to account for our incomplete understanding of gravity. But as more precise measurements were obtained, it became clear that a new fundamental element was required. And that's where gravitational wave astronomy began to play a crucial role. Gravitational waves, predicted by Einstein over a century ago, are ripples in space-time caused by accelerating massive objects, things like black hole mergers or neutron star collisions. Think of dropping a pebble into a still pond. The ripples spreading outwards represent gravitational waves. These waves travel across the universe at the speed of light, carrying information about their source. Detecting them is extraordinarily difficult because they are incredibly weak when they reach Earth. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo were built to detect these faint ripples. These instruments use incredibly precise lasers and mirrors to measure minuscule changes in the length of spacetime caused by passing gravitational waves. It's like having an extraordinarily sensitive ruler, capable of detecting changes smaller than the width of an atom. Initially, LIGO's primary goal was to confirm the existence of black holes and neutron stars, and to study their mergers. These events are incredibly energetic and generate strong gravitational waves. However, as LIGO's sensitivity improved, scientists began to look for something even more subtle, evidence of a cosmological signal, a background hum in the gravitational wave spectrum that could be linked to dark energy. The idea was that if dark energy is a property of spacetime itself, it might manifest as a specific pattern in the fluctuations of gravitational waves across a wide range of frequencies. This is where things got particularly complex. The cosmic microwave background radiation, the afterglow of the Big Bang, provides information about the early universe and its initial conditions, but that signal is relatively uniform. Gravitational waves, originating from events throughout the universe, could potentially carry information about the evolution of dark energy over time. Researchers started looking for a standard siren, a gravitational wave signal whose characteristics could be used to determine the distance to the source and, crucially, to probe the properties of dark energy. The challenge is that gravitational waves from distant events are extremely weak, and their patterns are often obscured by noise. More recently, detectors have begun to reveal a surprising and potentially revolutionary observation: analysis of gravitational waves from merging neutron stars, particularly the event GW170817, revealed a distinct feature in the signal: a slight damping of the gravitational wave amplitude at very high frequencies. This damping wasn't predicted by standard general relativity and is now thought to be directly linked to the effects of dark energy. The precise details are still being worked out, but the evidence suggests that dark energy's influence extends to the highest frequencies of gravitational waves, far beyond what was previously anticipated. This observation is hugely significant. It provides the first direct, independent measurement of dark energy's equation of state, a parameter that describes the relationship between the dark energy's pressure and density. The results are consistent with the cosmological constant model, which proposes that dark energy is a constant, uniform energy density inherent in space itself. However, the observed value of the equation of state is slightly different from what the cosmological constant predicts, leading to ongoing debate and research into alternative theories. The detection of GW170817 also triggered a multi-messenger observation: gravitational wave data combined with electromagnetic observations, light, radio waves, X-rays, offering a far richer understanding of the event and providing invaluable constraints on dark energy models. The study of gravitational waves and dark energy is still in its early stages, but it's rapidly becoming one of the most exciting frontiers in cosmology. As detector sensitivity continues to improve, and as new gravitational wave observatories come online, we can expect to gain an even deeper understanding of this mysterious force and its role in shaping the fate of the universe. The ability to listen to the universe through gravitational waves promises to fundamentally change our picture of dark energy, potentially unveiling its true nature and paving the way for entirely new physics. The prevailing cosmological model, lambda-CDM, built upon the observation of accelerating expansion, offers a remarkably successful description of the universe. Yet, the very existence of dark energy, the unseen force driving this acceleration, continues to present a profound puzzle for theoretical physicists. It's not a failure of the model precisely, but rather a glaring gap in our understanding of what actually causes it. The lambda component, representing dark energy, is a simple representation of a cosmological constant, a static energy density permeating all of space. However, this simplicity doesn't adequately address the fundamental questions arising from the data. One of the most persistent challenges lies in the observed value of dark energy. The cosmological constant, as initially conceived, predicts a value approximately 10 sub 12 slash sub times greater than what is actually measured. This discrepancy, often referred to as the cosmological constant problem, is a staggering magnitude. It's not merely a slight inaccuracy. It represents a difference of unimaginable proportions. The universe's energy density, according to our current models, should be dominated by this incredibly high value. Yet observations consistently point to a value around 10 sub 9 slash sub times the energy density of the vacuum itself. The reasons for this vast difference remain elusive, and it's a problem that has spurred numerous theoretical investigations. Several attempts have been made to bridge this gap. One approach explores the possibility of quantum fluctuations playing a more significant role than currently incorporated. Quantum mechanics predicts that even in empty space, virtual particles, particle-antiparticle pairs that spontaneously pop into existence and then annihilate, constantly appear and disappear. These fluctuations contribute to the overall energy density of space, but the calculations typically yield values far too large to match observations. The issue here isn't necessarily the presence of quantum fluctuations, but rather the way they are coupled to gravity. Another avenue of research delves into modifications to Einstein's theory of general relativity. The theory, while incredibly successful in describing gravity on large scales, might break down at the energy scales present in the very early universe, or at the extreme conditions near the event horizon of a black hole. Alternative theories, such as F-R gravity or tensor vector scalar TVS gravity, propose modifications to the Einstein field equations that could account for the accelerating expansion without invoking a cosmological constant. These models attempt to explain the acceleration through changes in how gravity behaves under different conditions. However, each of these modified gravity theories faces its own challenges. Many require introducing additional, often arbitrary, parameters, making them harder to test and less elegant than the simple cosmological constant. Furthermore, it's difficult to convincingly explain why these modifications would only become significant at the scales we observe today. The concept of dynamical dark energy also offers a compelling, though complicated, alternative. Instead of a constant energy density, dynamical dark energy proposes that the dark energy's properties, its equation of state, the ratio of its pressure to its energy density, can change over time. This could be driven by evolving scalar fields, dubbed quintessence, that interact with gravity. Quintessence models require specific potentials for these fields, and selecting a potential that accurately matches the observed expansion history is a considerable task. The problem is compounded by the fact that any small deviation from the standard lambda-CDM model can lead to significantly different predictions for the universe's future. Then there's the possibility that our understanding of spacetime itself is incomplete. General relativity treats spacetime as a smooth, continuous fabric. But what if, at extremely small scales, perhaps on the order of the Planck length, the scale at which quantum gravity effects become dominant, spacetime isn't smooth at all, but instead possesses a granular, foamy structure? Such a structure could dramatically alter the way dark energy interacts with gravity and could potentially explain the observed acceleration. This is a realm where theoretical physics and cosmology converge, attempting to unify the very fabric of reality. Another intriguing consideration is the possibility of large-scale inhomogeneities influencing the apparent acceleration. Perhaps the universe isn't as uniformly expanding as we currently assume. If there are vast, unseen voids or clusters of galaxies that are moving away from us at different rates, it could create the illusion of a uniform acceleration. This idea, however, requires exceedingly precise measurements and remains largely speculative. Finally, there's the nagging question of whether we're simply missing something fundamental about the universe's composition. It's conceivable that there are other, yet undetected, particles or fields interacting with dark energy in ways that we haven't yet accounted for. Perhaps a previously unknown type of field is responsible for the acceleration, and we're only seeing its effects through gravity. The quest to understand dark energy is, in essence, a quest to understand the very nature of the vacuum itself, a space that, according to our best theories, makes up approximately 95% of the universe. It's a truly profound mystery, and physicists continue to explore its implications, pushing the boundaries of our knowledge and challenging our fundamental assumptions about the cosmos. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed into the vastness of dark energy, contemplating its mysteries and our place within the universe. Let your thoughts drift now, calm and unhurried, like stardust settling into the velvet of night. Allow your mind to find its ease, seeking the comfort of slumber.